Hello everyone. So this is the next video on real analysis. We will be discussing differentiability of functions of several variables. So here several variables in the sense f from Rm to Rn, where n is greater than or equals to 2. So it is not here. Already we discussed what will happen to the differentiability and continuity of real valued functions, which is a scalar valued functions of real variable. However, in order to visualize these functions of several variables, first we will restrict ourselves to n equals to 1, whereas m can be any integer. In fact, strictly speaking, we consider m equals to 2 and n is equals to 1. Later on, we can extend the idea of same to functions of several variables of more than 2 variables, and which is a vector valued function. That can be thought once you have the idea of the scalar valued function, in the sense you take n is equals to 1, then we try to visualize the things, we can extend the same idea. So here, as I said, I am considering m equals to 2 and n is equals to 1. When we say that the function is differentiable, see, f is defined from a subset of s of r square to r, in the sense this function, this function, this is a scalar valued function, since whatever your function f of x comma y is given a scalar, is assigned a scalar value, so you are quantifying the particular function to a scalar. Now we say, look to this, f of a plus h comma b plus k minus f of a comma b equals to ah plus bk plus square root of h square k square minus into e of h comma k. So this e of h comma k is called error function, and a is the partial derivative with respect to x, b is the partial derivative with respect to y. If you have this particular equation, if this error function is tending to 0 whenever h and k tends to 0, I repeat, whenever this error function tends to 0, this e of h comma k must tend to 0 whenever h comma k tends to 0. If that happens, we say that f is differentiable at this point a comma b, where h and k are small step sizes or small values with respect to x, h and small value or else a small change in x, this the small change in y. Idea is clear? Once we solve few problems, we can understand what exactly is this. So f is differentiable at a comma b if and only if that error function tends to 0 as h comma k tends to 0 comma 0. Now he is asking f of x comma y equals to x square plus y square. Verify whether f is derivative exists. F is differentiable at 1 comma 2. So we need to verify this. What will happen to this f of xy equals to x square minus y square? See, and I have mentioned one remark here. Any polynomial, in the sense, if you have x square plus y square or else x cube plus y cube, some f of x comma y is a polynomial, then the function is differentiable. So here it's a polynomial, so this function is differentiable. In fact, let us try to show by using this definition of the error function. So it says, practice it so that you can once or twice you need to recall this whenever you are free. That will help you to memorize the formula well. So this is the formula what we want. So a is 1 and b is 2. In fact, this small a points are a comma b is 1 comma 2 And what is this a and b? No need to calculate fx and fy using the formula, since it's a polynomial. Fx is 2x, fy is 2y. What is a? A is fx at the given point. So fx at 1 comma 2 means it is 2. B is fy at the given point, so it is 4. So we know a and we know b, and we know what is f of h comma k. H comma this is f of 0 plus h 0 plus 1 plus h 2 plus k minus f of 1 comma 2. This is 2 into h plus b is 4 into k, square root of h square plus k square. H we know, h square plus k square e of h comma k. See, you need to keep h and k as it is throughout, because that's what we need to show. Later we make them to tend to 0, then we will check what will happen to this error function. So now this is 1 plus h comma 2 plus k means 1 plus h whole square plus 2 plus k whole square minus f of 1 comma 2. So 1 plus 4, it is minus 5, which is equals to 2h plus 4k plus square root of h square plus k square, error function e of h comma k. This is 1 plus h square plus 2h plus 4 plus k square plus 4k minus 5 equals to 2h plus 4k plus square root of h square plus k square e of h comma k. So here 4k goes with 4k, 2h goes with 2h, and I have 1 plus 4 is 5, 5 goes with this 5. So I have h square plus k square equals to square root of h square plus k square e of h comma k. This implies e of h comma k is h square plus k square square root, and this tends to 0 as h comma k tends to 0. That means f is differentiable at 1 comma 2. Idea is clear? Second problem, f of x comma y equals to modulus of xy. See, first we need to find a, that is fx at 0 comma b 0, and b fy at 0 comma 0. Fx is limit as it tending to 0, f of a plus h, that is 0 plus h comma 0 minus f of 0 comma 0 by h. Limit as it tending to 0, f of h comma 0 minus f of 0 comma 0 by h. See, f of 0 comma 0 is 0, so f of h comma 0, that is also 0. So 0 minus 0 by h, so it is 0. Similarly, fy is also 0. So if the partial derivative is 0, at 0 comma 0 again it is 0. So a is 0 and b is 0. Idea is clear? Now you need to have that formula f of a plus h b plus k minus f of a comma b equals to ah plus bk plus square root of. Now what is this? A is 0, so it is h comma k minus f of 0 comma 0. A h is there. A is 0, b is 0, square root of h square plus k square. F of h comma k is modulus of hk. F of 0 comma 0 is 0. See, once you have this kind of problems, the better way to look into this is by going into the polar form. In the sense, you can visualize this as e of x comma y equals to xy by square root of x square plus y square. So put x is equals to r cos theta and y is equals to r sin theta. So this will be r square cos theta sin theta by r square root of r square, which is as good as saying r. So this is r into cos theta sin theta and then to 0 as theta is tending to 0, or else r is tending to 0. So your error function e is tending to 0. As r tend to 0 is as good as saying x comma y are tending to 0. So in the sense error function is 0, so this function is differentiable. Here I changed h comma k to x comma y since we are very familiar with this notation, or else you can say put x is equals to r cos theta and k is equals to r sin theta. It doesn't matter. So third problem, here is given is not differentiable at 0 comma 0. So you should always keep an eye on these kind of problems. Modulus of xy is continuous. If you take the square root, it is not continuous. Sometimes these standard examples will help us to eliminate the options in the examination. F from r square to r, f of x comma equals to modulus of xy. See, for this we need to find in fact a and b, and already we solved this. A is 0, this at 0 comma 0, and b is fy at 0 comma 0. This is also 0. So your error function e of h comma k is modulus of hk by square root of h square plus k square, or else e of x comma y equals to xy x square plus y square. So put y is equals to mx, you will get x into mx x square plus m square x square. So it is x square root of m x. So it depends upon m. That means this does not tends to 0. In the sense the function is not differentiable. It is clear. Fourth problem, f of xy is equals to modulus of f of x comma y equals to modulus of x plus y at 0 comma 0. See, this function, in fact in the function of scalar valued function mod x was not continuous. This is not differentiable here also. F of x is equals to modulus of x plus modulus of y, because the partial derivative itself does not exist. If I say a is equals to fx at 0 comma 0, it implies limit as h tending to 0, f of 0 plus h comma 0 which implies, because it depends upon your h. If h is positive you will get 1, if h is negative you will get minus 1. So this value does not exist. So this function is not differentiable. Fifth problem, f of xy is equals to x square y square sin of 1 by x square plus y square. See, many a times if we ask us to find verify differentiability, first verify the continuity. If the function is continuous, then we can move further. If it is discontinuous, then we can conclude then and there, because every differentiable function is continuous. So here f of x comma y equals to x square plus y square sin of 1 by x square plus y square. So f is continuous in fact. At 0 comma 0. See here, one thing you need to understand, we are concentrating the continuity at 0 comma 0. Does it implies we are least bothered about the other points? In the sense, see, if the problem for this particular given function is at the origin, ನೀವು origin in ಹೊರಗಡೆ ಬಂದ್ಬಿಟ್ರೆ function is defined, so it will be continuous. ಅರ್ಥ ಆಗುತ್ತಾ? So this is the continuous function if you come out from the origin. This is also a continuous function if you come out from the origin. So the product will be continuous. So only the bothering fact is near origin. So we are concentrating at 0 comma 0. ಅರ್ಥ ಆಗುತ್ತಾ? Okay. Now, so as usual, since I have x square, y square, put x is equals to r cos theta. And y is equals to r sin theta. So you will have x square plus y square is into sin of 1 by x square plus y square, which is r square into sin of 1 by r square. See this function, as r tends to 0, this is 0 and this is bounded. So we have the results. If you have one term which is converging, going to 0, approaching to 0, and other is bounded, so this will tend to 0. So the function is continuous near 0. But we need to think about the differentiability. For differentiability, the same formula we need to use. Before that, we need to find the partial derivatives. What is a? Let me find fx first. Fx is limit as h tending to 0, f of x plus a plus h. A plus h is 0 plus h. H comma 0 minus f of 0 comma 0 by h, which is limit as h tending to 0, h square sin 1 by h square by h. So it is limit as h tending to 0, h into sin of 1 by h square. This will tend to 0 as it tends to 0. Same reason. So similarly, your fy is also 0, since the function is, you have wherever x is there, the same power is there for y. So if that happens, we can say the same is true for y. So now the formula for differentiability is this: f of a plus h comma b plus k minus f of a comma b equals to ah plus bk plus square root of h square plus k square e of h comma k. So this is hk minus f of 0 comma 0 equals to, this is 0, this is 0, and square root of h square plus k square e of h comma k. F of 0 comma 0 is given as 0, so you will have h square plus k square sin of 1 by h square plus k square equals to square root of h square plus k square e of h comma k 1 by 2. So I have, this is square root of h square plus k square sin of 1 by h square plus k square, and as h comma k tends to 0, this will tend to 0 and this is bounded, so this will tend to 0. So error function will tend to 0. So the function is differentiable at 0 comma 0. Idea is clear? Yes. See, this is sixth problem. is f of x comma y equals to x square y, x to the power 4 plus y square, and whenever it is you are near at the origin, the function is 0. Is asking check the continuity, differentiability at 0 comma 0, and the existence of directional derivative. This problem is important in the sense it will give is there any relation between these three things. See, we need to find the continuity. However, as I discussed for the last problem, see x square y by x to the power 4 plus y square. Here where we need to check the continuity, y is asking at only at 0 comma 0, because the function, see, this is a polynomial and this is also a polynomial, and this is defined, this is non-zero if you are coming out of this, that is x comma y is 0 comma 0. If you just come out from the origin, this is non-zero and this is also non-zero. So in the sense, the quotient of two polynomials is continuous. Idea is clear? So the function is continuous everywhere, but we need to check whether it is continuous at 0. Only that point is remaining. So if we find, see here, if y is equals to mx square, I will have x square into mx square, x to the power 4 into m square, x to the power 4. So this is m by 1 plus m square. So it depends upon m, so the function is not continuous. If it is not continuous, it is not differentiable. So the given function is discontinuous and not differentiable. But what can you say about its direction derivative? See, let me consider the vector to be u1, v2, u1 and u2, and we know the direction derivative at the given point a comma b is a plus h into u minus f of, say this is p by h. So this is the direction derivative, limit as h tending to 0. Then the point is a comma b, a plus h u1, b plus h u2 minus f of a comma b by h, limit as h tending to 0. F of, what is a? A is 0, so this is h into u1, h into u2 minus f of 0 comma 0 by h. So here we are choosing u1 into u2 is non-zero, because the given function, see, the direction derivative exists in fact for all among all the direction, but if you come approach 0 from x and y, the direction derivative, there is, we need to check. That's why we are choosing u1 and u2 is non-zero. Idea is clear? u1 and u2 must be non-zero. Now this implies limit as h tending to 0, f of h into u1, h into u2 is there, so just plug it over there, h square u1 square h u2 by, I have h u1 whole to the power 4 plus So this is h cube u1 square u2 by h to the power 4 h to the power 4. I will take this h here, so it will be, if I take h square out, this will become h cube, right? H square u1 to the power 4 plus so this is u1 square u2 h square to the power 4 u2 square, limit as h tending to 0. If h tends to 0, this is u1 square u2 by u2 square. So this is u1 square by u2. Just assume, think about this. Since we know u1 and u2, so the directional derivative exists in all the direction. In the sense, if the function is not continuous, then the directional derivative exists in all directions. So in the sense, for existence of directional derivative, even continuity is not needed. So here I have one more problem. You can just work it out. The same problem, but I choose f of x comma y equals to xy square x square y to the power 4. This also in the same way we will get the function is not continuous, so and this is not differentiable. However, the directional derivative exists, and this is u2 square by u1. Kindly check this for this given problem, and we will by these two problems we have one observation. If f is differentiable, that we know already, that implies f is continuous. If f is differentiable, this implies f has directional derivatives. If directional derivatives exist in all directions, then continuity may or may not be possible, right? Because the last problem is the same. The directional derivative exists in all directions, but the function is discontinuous. Continuity is also not necessary. Idea is clear? Thank you.